Okay, so with all of this in mind, let's just first think through the two different things that Bill needed to have happen for his candy apple recipe that works. And then I'm going to try to walk through what the basic physics of this is that leads to that. So the two things that he needs are that number one, he needs when the candy apple solidifies that it's actually a solid, that it has some rigidity to it, that it's got an elastic modulus, that it's not too brittle, so that, he can serve it in a state dinner or whatever context that he would like to serve it. The second thing that he needs, and that of course will happen when it cools sufficiently that you can actually serve it and you can pick it up without burning your hands. The second thing he needs is that when the material is hot, it needs to flow. It needs to be like a liquid. It needs to be such that he can actually mold it, so that he can basically mold the candy apple with his hand and make it into the shape that he wants. Those are the two different ingredients that he needs. And what we now need to think through is what has to happen to the molecules in the sugar-water solution for this to occur. And so let me just try to walk you through the scenario, and then I'm going to try to indicate as we do this how the scenario would change if you were to change, for example, the initial temperature of the sugar-water solution, so that instead of 150 degrees, it were some other, perhaps lower temperature. I just want you to get a flavor for what would change. So let's suppose that you're at 150 degrees. So what you do is you take, as Bill did, you pour it onto a cold substrate. The material starts to cool. The amount of sugar that's in solution is much more than it should be, so that crystals start to form. When you're at the high temperature, 152 degrees, the sugar is dissolved, but there are still little nuclei of crystals that are floating around. Now, we've talked about nuclei before when we explained Joan Roca's beautiful dessert with the supercooling. We told you that actually little crystals are needed to actually form, to actually start crystallization. And these little crystals of sugar are what are present, in sugar-water mixtures at any temperature. And when you're at high temperatures, there aren't very many of them because the sugar really likes to dissolve, but there are some that are floating around. And when Bill quenches the mixture by pouring it on the table, those little sugar nuclei form as nucleation sites, and sugar crystals start to grow. Now, they grow rather rapidly because the material was very hot, and so there's really a lot of sugar that's dissolved in the solution, which is now is much cooler. It's something like the temperature of the table. Those sugar crystals grow, and you then have these big solid chunks that are floating around this liquid. They're solid. They have an elastic modulus. They obey an equation like the one that we've described this week, and they're floating around the liquid. Now, the amount of liquid there is, of course, is also determined by the temperature that you started at. It's determined by the 150 to 152 degrees. That, as I already told you, tells you the fraction of liquid that there is in the bath. So what you've got now are these crystals that are floating around in what's really going to be a rather small amount of liquid, and that's what determines the material. Now, if the crystals were, if the only ingredient that were in the solution were sucrose, then we know what happens to sucrose when you let it equilibrate under those conditions. It will reform the sugar that it was in the first place. It will just reform sugar crystals, right? And that actually, sugar crystals are wonderful things. You can crunch them with your mouth, but they don't actually happen to flow. They don't have this malleable property that Bill needed in order to mold it like he did. In order for that to happen, the system has to form a glass. And so a glass formation requires that you put something in to impede the crystallization of these nuclei that are growing. And it turns out that that's the role that glucose plays in this process. That is, glucose, as I told you, is really a part of sucrose. Sucrose is a disaccharide which contains glucose and fructose. And glucose is just like a little part of sucrose, which is going to stick to the sucrose molecules in just the same way that the sucrose molecules stick to each other to form the crystals. But its problem is it has a sort of weird shape. It's sort of like if you did the following thing. Imagine you took a bunch of blocks that were perfectly square blocks, and we stacked them up to make a block wall. It's like, a brick wall that you might have, that makes part of your house. You can stack the bricks up, and it makes a perfect lattice of bricks. But now suppose somebody came along and said, oh, I'm going to take a little part of the bricks away. And so you clunked off a segment of the brick. And if you tried to build the house out of these bricks that weren't perfectly square, then they won't stack as well, and it's not going to be as good of a solid. That is, you wouldn't want to build your house out of those materials. And in the same way as if you throw into the solution pieces of sucrose, namely glucose, that aren't the sucrose itself, it won't form as strong or as rigid a solution, and it will be better able to flow. That's the role of glucose. It's essentially an inhibitor of crystallization. There are other ingredients that could play the same role that Bill that people do use to make different types of candy that weren't appropriate for the candy glass. I mean, so for example, corn syrup plays the same role. It's not a piece of sucrose, it's actually many sucroses that are stuck together. They're chains of sugars, which basically play the same type of role, although the detailed behavior can be a little different. Anyway, so with that, Bill was able to mold the glass, and he made a glass, and he was able to mold it and make it into the candy apple that he ended up with, which solidified in this very hard phase. Now, and that's essentially the physics of the recipe. Now, the last thing that I want to end with here is to just think through a little bit what would have happened if he had started at a different temperature. And since 150, 152 degrees is pretty much the hottest you can go to when you're playing with or cooking with sugar water solutions without burning it or something, let's just imagine for the sake of argument that the mixture was at a lower temperature. So suppose you were, in the, say, firm ball stage or soft ball stage where, right, where when you dunk a scoop of it and put it in, when you quench it, it actually has itself an elastic modulus. I mean, it basically is squishy when you let it cool. So let's imagine what would happen there. So again, you're starting out at a lower temperature, so maybe we'll say it's 120 degrees Celsius, just for the sake of argument. You do exactly what Bill did. You imagine pouring it on the substrate, and it will pour outwards. And then, of course, it will start to cool. It will cool down to the temperature of the substrate. The mixture is, as before, super saturated. There's more sugar dissolved in the mixture than actually equilibrium can support. There are going to be more crystal nuclei in the initial state than there were at very high temperatures. There will be more of them simply because since you're starting out at 120 degrees instead of 150 degrees, it's going to be easier for the nuclei to form because there's not as much heat to agitate them and break them apart. So you will have more crystal nuclei in the initial pouring. But those nuclei will grow more slowly than they did initially because there's not as much sugar that's dissolved in the solution as there was in the high temperature version. So if you sort of manipulate that as Bill was manipulating his, then what you will form are lots of little crystals instead of, so there will be very many little crystals as opposed to, a few bigger crystals which would form in the mixture that Bill made. And those little crystals, and there's also going to be, of course, more water around, simply because the boiling point, the mass fraction of sugar at 120 degrees is much lower than that at 150 degrees. And so you're going to have lots of little crystals, and you can just imagine drawing it in a background of water. And that material actually is squishy. It isn't as solid. It has an elastic modulus, but it actually flows, and so it's not as hard as the candy mixture that Bill used. And actually, you can't use it to make the shell of a candy apple. Why? Because if you tried to make the candy apple that Bill made using sugar water that started at this lower temperature, it would just basically flow enough so that it would come apart. It wouldn't remain a solid mass. And so while it's easier to mold at room temperature, it also doesn't hold its form at high temperature. That is, it doesn't remain a solid. So later on, we will come back to this fascinating story of sugar-water mixtures when we move to the viscosity stage of this class, and you will start to see how these different shapes of crystals and amounts of liquid that the crystals are moving in really control in a fundamental way how the material flows. But for now, for this week, what we want you to focus on is the elastic parts of what's happening. And you should see that with these very simple molecular ingredients and the interactions between them, one can really, if one knows what it's doing, create remarkable solid bodies like, for example, Bill's candy apple.